Greetings, Physics 3310 students. Today we are talking about ANOVA. This will not be covered on the final, and there is no homework assignment on this information. This is just completely for your information, for you to be able to use this technique in the future as a scientist. So what is ANOVA? It's an acronym that stands for Analysis of Variance. It's what you do when you have a bunch of different histograms and you compare them to each other, basically. So it is a tool or a test to ask this question: is the difference between 3 or more groups statistically significant, where each group is a histogram? A one-way ANOVA only tests the variance of one variable. And so what we're doing with one-way ANOVA is asking the question, is the mean the same for these different groups, for these different histograms? Do they have the same mean or not within their histogram ranges? Okay, so if you need to go back to histograms and distribution functions, go check that lecture out. That's where we discussed how to compare just two groups, just two histograms to each other. Are these two means the same or not for these two histograms? And we did the t-test to ask that question. Now we're going to ask about more than two groups. Are those means the same or not for more than two groups? So for general purposes, what does ANOVA do? It tests whether the means are the same or not from different groups. And those groups are going to be samples from different populations. Samples have a specific meaning and populations have a specific meaning. So a population represents all the constituents of a group. Like, for example, women born in the United States between 1975 and 1985. You can't survey that entire group, that entire population, so you would choose a representative sample of that population. Like 100 women born in the US between 1975 and 1980. You have to assume that your sample accurately represents the population when you're doing this. Okay, so that's what those vocabulary words are. When we're using ANOVA, we are testing a null hypothesis. If the null hypothesis is true, that means there is no statistically significant difference between the sample means. For all the groups, we are comparing the means of each group to the rest of the means of the groups. Okay, if the null hypothesis is not true, that means at least one of the means from the groups has a different mean from the other groups. All right, sounds like a bunch of words, I know. So we're going to illustrate this with an example that first we're just going to look at this picture to understand what the example might be. Here we have some examples of histograms: a blue histogram, a pink, and a green histogram. Each of these histograms has a mean value indicated by the vertical dashed lines, and each of these histograms has a width that might be different from one histogram to the other, indicated on the green one with a horizontal dashed line. So we have also indicated with these labels that the variation between the groups is what is being compared when the means are compared to each other, and the variation within a group is what we are considering when we consider the variation in one group. So to claim a statistically significant difference between this mean and this mean and this mean, the variance between the group sample has to be large enough to overcome the natural variation within the groups, which we standardize with, or we quantify with standard deviation. Okay, even more specific example to help us understand. Let's pretend the blue histogram is the fitness score for 500 men aged 50 to 59. And the red pink histogram is the fitness score for 500 men from age 40 to 49. And let's pretend that the green histogram is the fitness score for 500 men aged 30 to 39 years old. Completely made this up just to help us illustrate what all these words mean. It could be, true that the 50 to 59-year-olds are going to have a lower fitness score than the 40 to 49-year-olds, and then the 40 to 49-year-olds are going to have a lower fitness score average compared to the 30 to 39-year-olds. And then there's going to be variation within each population. For the 30 to 39-year-olds, it looks like maybe there's more variation. And for the 40 to 49-year-olds, there's less variation and even less for the 50 to 59-year-olds, whatever. In this case, this is made up. So what we're asking with this null hypothesis test is that mean fitness score for the blue and for the red and the green, are those the same or not? Are these wide enough? Are these histograms wide enough for us all to consider those the same mean, or are they different means? Is the mean fitness score the same or not for these three sample groups? Or is the difference between the mean fitness scores for these sample groups statistically different? So our null hypothesis is, for this specific example, there is no statistically significant difference between the mean fitness score something's not right there. Okay, I fixed that. The null hypothesis is there is no statistically significant difference between the mean fitness score for these three sample groups. Is that true or is that not true? Is what ANOVA is going to help us answer. So it's another yes or no question, basically, that we are answering with ANOVA. So to perform ANOVA, to answer this question, this yes or no question, first we have to calculate this quantity, the F statistic. The F statistic is the variation among the sample means. So how different are these means from each other compared to the variation within the groups? So compared to the standard deviation of each group, somehow considered together. So to calculate the F statistic, we examine this F distribution. It is a probability distribution function. It's a new distribution function we haven't learned about yet in this class. You don't really need to worry too much about the expression for the F statistic distribution function. You just are going to use it to determine, the answer to this yes or no question. So it has the F value along the x-axis and the probability density along the y-axis. It's a probability density function, so that means if we integrate this function from 0 to infinity, we're going to get 1. The F curve always comes to a maximum quickly after 0 and then has a very long tail out to infinity. Okay, so because this is a probability distribution function, yes, it's going to integrate from 0 to infinity to be equal to 1, but also an area under the curve is going to give us the probability that a value is going to fall within that integrated range. So in this image, the area that is red is equal to 0.05. Area under the curve is equal to 0.05. That's going to correspond, so this F value being 3 or above is going to correspond to a probability of 0.05. There's a 5% chance that F is 3 or above. This 5% is a common threshold. If the F statistic number is greater than 3, then the probability of statistically significant differences is smaller than 5%. So this F factor, this F number, the probability or the area under the curve dictated by the F statistic tells us the probability of whether or not our means are statistically significantly different or not. Okay, so if the F statistic is greater than 3, if we calculate F and it's 3.2, or it's 3.5, or it's 4.7, any number above 3, then this would imply a failure of the null hypothesis, because the chances that the means are different is very, very low, less than 5%. Okay, let's look back at our fitness score example and understand how we can apply this null hypothesis idea. The null hypothesis, let's remember, is that, the null hypothesis is there is no statistically significant difference between the mean fitness scores for these 3 sample groups. Or that's us saying the sample means are the same, statistically speaking. We're saying that this is wide enough, and this is wide enough, and this is wide enough, that they basically all overlap with each other and the means are the same. So let's see if that null hypothesis is correct for our fitness score example. Let's say we calculate F equals 4. If we calculate F is equal to 4, then the probability that the sample means are the same is less than 5%. And we're going to say that our null hypothesis has failed, which means that the mean score for the 30 to 39-year-olds is different, maybe, from the 40 to 49-year-olds or the 50 to 59-year-olds. Or the 40 to 49-year-old group has a different mean from the 50 to 59-year-old group or the 30 to 39-year-old group. The only thing we've shown is that the sample means are not the same, but we don't know which ones are not the same. We just know that one of them is not the same as the others when our null hypothesis fails. Okay, we need to have some assumptions correct before we can really use this test. Our samples need to be independent and the errors need to be random only. That means our distributions are going to be Gaussian, which allows us to use this analysis technique. They're Gaussian because the errors are random only. We also need the standard deviations of the groups to be not super different from each other in the first place. If they're super different from each other, we can't really use this test. So we need the largest of the standard deviations to be no more than 2 times as large as the smallest standard deviation in our set of groups, in our set of samples. We are going to define some variables here to be able to calculate that F statistic number. K is the number of groups, so that was 3 for our fitness test example. X sub I is the mean of each group, the mean value of each group. X bar, sorry, that was X bar sub I. X bar is the mean of all the samples considered together. S sub I is the standard deviation of each sample group, shown down here. Remember, that's the square root of 1 over n sub I minus 1, where we add up x sub I minus x sub I mean, and we square that quantity. This is different than sigma sub I because S sub I is for each group, not for an entire set of samples. N sub I is the sample size of group I, and N is the total number of samples. Okay, so we're going to take those definitions and apply them to this F statistic calculation. Remember, F is the variation among sample means. How different are the means from each other, divided by the natural variation within the groups, so some measure of standard deviation of the groups. So that is actually equal to the mean square for the groups divided by the mean square error. The mean square for the groups is going to be the difference between the average the mean per group minus the overall mean, quantity squared, times the number of points in that group. We're going to add all that up, divide by k minus 1, where k was the number of groups. Okay, so that's our numerator of F. And then our denominator, the mean square error, is the number of points in that group minus 1 times the standard deviation of that group squared, adding all of those up for the groups divided by n minus k. The total number of samples minus the number of groups. We put all that together. Here is the F statistic calculation equation. Okay, we're going to do an example. Say we have a researcher measuring weight loss for different groups. Program 1, Program 2, Program 3. Those are our different groups. Do these groups have the same mean weight loss, or are those means different, statistically speaking? Okay, so we copied the data up here on the top of the slide. There's 3 groups. The first mean is 7, the second mean is 9, and the third mean is 15. The mean of the total is 10. Take all of them and take the mean, that's 10. The variance per group squared is 2.67 for the first group, 4 for the second group, and 9 for the third group. That's the standard deviation squared, sorry. This quantity here per group. So the variance is the standard deviation squared. Okay, then we have the sample size per group. That's 4 points, program 1, 3 for program 2, 3 for program 3. The total number of samples is 10. We're going to take those quantities and copy them to the top of the page here. Then we're going to calculate the mean square for the groups and the mean square error. The mean square for the groups is 57, following our function we already described, and the mean square error is 4.86, again following the algorithm that we recently explained. We calculate 11.74 as our F statistic for this group of weight loss data, this set of weight loss data for these 3 groups. We calculated 11.74. Okay, so that's a lot bigger than 3. Our F value is way over here, off the screen. So that means the probability that the sample means are the same is way less than 5%. The null hypothesis has definitely failed, and at least one group here does not have the same mean weight loss as one other group. They do not have the same means for this example. Okay, now let's think about that F distribution. It always has the same general shape. It comes to a maximum quickly and then slowly decays as the x-axis gets bigger. But the location of the maximum and the length of the tail are going to be controlled by different variables. these variables are referred to as the degrees of freedom for the numerator and the degrees of freedom for the denominator. Okay, so they're listed here, numerator degrees of freedom, denominator degrees of freedom for different f's. So if the degrees of freedom in the numerator are 3 and 5 in the denominator, your curve is going to look like this, your f statistic curve, f distribution. If you have 90 degrees of freedom in your numerator and 10 in your denominator, your curve is going to look like this. So that is going to change how your f distribution curve looks. So how do I find the degrees of freedom? The numerator, degrees of freedom, is k, the number of groups, minus 1. The denominator, degrees of freedom, is going to be n, the number of total samples, minus k, the number of groups. For our example, the degrees of freedom for the numerator, k minus 1, is going to be 3 minus 1 equal to 2. For our denominator degrees of freedom, we're going to have n is equal to 10, total number of samples, minus k is equal to 3, the number of groups, so that degree of freedom is 7 for our denominator. If we plot our f distribution in Excel, it's going to look like this, for degree of freedom 2 in the numerator and degree of freedom 7 in the denominator. So here's our probability density. Our value of f is 11.74, way out here. So that means, again, having an f value that high isn't very likely. Again, we can reject our null hypothesis. At least one of the means is different from one of those programs compared to the other two. Now, this is when you can use software to make things easier for yourself. For example, Excel. You can use Excel to return the probability that the f statistic is 11.74 or higher, called the p-value. In Excel, you would enter the command fdist 11.74 to 7. So remember, 2 is your numerator degree of freedom, 7 is your denominator degree of freedom, and 11.74 was what we calculated for f. That is going to return us a value, a p-value of 0.0058. That means if we integrated the f distribution starting at 11.74 and went out to infinity from there, we would get 0.0058. So there's a 0.58% chance that the value would be that high if the null hypothesis were true. That is a very, very, very low probability, so we can reject the null hypothesis. Usually we compare to a threshold like 5%, like we mentioned earlier. Since 0.58 is less than 5, we can reject the null hypothesis. Sometimes people use 1% here as their threshold, depending on the situation. You can also use tables to look this up rather than use Excel. So if you want to use a table, you would find the numerator degrees of freedom on the top, denominator degrees of freedom on the side, and then read off the f statistic for your situation. This table is from the Mind on Statistics report, Mind on Statistics textbook, and it reports the value of the f statistic at the critical or comparison value. Since 5% is really common, this table gives the f statistic that corresponds to a p-value of 0.05. So what that means is if your value of f is larger than the one in the table, then you reject the null hypothesis for the given degrees of freedom for the numerator and degrees of freedom for the denominator. 11.74 is bigger than 4.74 for our 2 degrees of freedom. So again, we reject the null hypothesis. So it's just another way to determine. Okay, let's summarize here. In order to perform ANOVA, you need to calculate the F statistic. So first you need to identify and calculate all your variables, which are K, N, the group means, the group standard deviations, the overall mean, the numerator degrees of freedom, and the denominator degrees of freedom. You're going to substitute all of those into the formula or look that up on a table to calculate your F statistic. Then you're either going to use Excel or another program to find the p-value for your F value. You compare the p-value to your threshold, which is usually 5%. If the p-value is less than 5%, you reject your null hypothesis and your means are not the same. You can also use tables to find the threshold value of F for your desired level, which is usually 5%. And then if F is bigger than the threshold F value, you can reject the null hypothesis, meaning the means are significantly different, statistically significantly different. Okay, that's where we're going to stop. I hope you enjoyed this exploration of ANOVA and hope you get to use it someday in your scientific careers. Bye.